So hello and welcome to everybody to this webinar about how do you degrade from a 2 out of 3 to a 1 out of 2 safety architecture and remain the same safety and process availability. This is one of the many topics that we covered during this kind of events, and considering the good feedback that we're receiving so far from the participants, we continue sharing our knowledge about intrinsic safety and functional safety.
Can I just disturb?
Yep.
Very quickly, I got
Yes.
here a message from someone saying he cannot hear us, but I guess the rest can hear us. Can maybe the other
I
one?
can hear you.
Yeah. Okay, so it's most likely the setting for this one person. I will answer this. Okay, thank you. Sorry.
A brief introduction about myself. I am Gabriele Caglio. I'm a technical support specialist here at GMI, and we have Tino van der Kapel, which is the expert and today's main speaker. I would like to start with an introduction of GMI for whom doesn't know us. GMI is an Italian company providing field interfaces related to intrinsic safety and functional safety. This means that it is possible to find GMI devices in many industrial packages, such as TCS, ESD, fire and gas, and so on. And we are talking about oil and gas, of course, petrochemical, pharmaceutical, mining, food and beverage, and many other industries. We have 40 years of experience in the field. The headquarters is in Italy, where we have our main facility and where we design, produce, and test all our products. As you can see now here, we also have several offices and resellers all around the globe, so we are available pretty much everywhere.
I think, Gabriele, something went wrong. As I was answering this question to this person, I saw the slides were advancing, so it was probably from my side that I disturbed your presentation. Sorry for that.
It's not an issue. It's not a problem. Don't worry. And as I mentioned before, here we are a safety company. We aim to provide safety and reduce the risk of hazardous events to safeguard people, assets, infrastructures, production processes, and the environment too. For this reason, the quality aspect of our product cannot be overlooked. We design our product, we manufacture and test them all internally, meaning that we do not outsource any of these tasks. This is why we are confident with about the quality of our products. Couple of more slides before to get into the real part of the webinar. One is about the certificates, or at least the certification bodies we are dealing with. This guarantees the quality of the devices, but also guarantee that GMI products comply with the market requirements according to different local regulations. Sorry. Going back a second, because I want to give you a brief overview of our portfolio. As I mentioned, we have intrinsically safe barriers. We have safety relays certified with and without light monitoring for energized to safe and de-energized to safe application. We have isolators and AX power supply systems up to SIL 3. We have then temperature and digital multiplexer for zone 1 installation. We have customized termination board for an easy connection to the main PLC and DCS system. We have ARC multiplexer surge arresters. And then we also provide consultancy and share our experience through courses related to functional safety and intrinsic safety. The final slide is about some of our customers, which stretch from system vendors, APC, OEM, and end users. Last thing I would like to say about the webinar in general is that the webinar is recorded and you will find it available on YouTube in a few days. You can subscribe on our channel to get a notification. You will get a link to download a PDF copy of this presentation in a couple of days from now. And also you will get a certificate, but only if you attend at least 75% of the webinar. If you have any question during the webinar, you can write it down in the Q&A session and we'll try to answer. So, Tino, please, they're all yours.
Thank you, Gabriele. I've seen in the meantime that this one person solved a problem, but now another person is writing that audio is a problem. He said it's very hard to hear you guys. So if this person can still hear us, I would recommend to log out, log in again and see if this would work. Otherwise, there may be a local problem on your platform, as we have many people listening into this webinar and there is no one answering. And thank you for the other person saying, I can hear you very well. So that's also what I assumed. Anyhow, topic for today is something to do with the architecture of your field devices or of your architectures of your safety loops. And the question is, or the title is, how do we degrade from a 2 out of 3 to a 1 out of 2? If you look back into the functional safety standard called the IEC 61511, which is the application-oriented standard to design a safety instrumented system, to maintain a safety instrumented system, and also to operate a safety instrumented system. And the topic we tackle here today is actually coming back in all those, let's say, life cycle phases, which I highlighted here with a red square. That means that the first time that you will come across the question, what type of architecture do we really need, is in phase number 3, which is highlighted here. This number 3 here in the left bottom corner, that is called a phase number. That's a phase activity of the life cycle from the IEC 61511. And this is in the safety requirement specification or in your SRS. So when you have your safety requirement specification, in your specification of your design of your safety instrumented system, that is where you come first across to the question, what type of hardware fault tolerance, what type of redundancy, what type of availability for safety and or availability for process do we really need on this specific unit or this specific loop. Of course, it goes without saying that this will also go across into your design phase, which is your phase number 4. That is where you physically will start to design and engineer your safety instrumented system. So, of course, based on the requirement specification, the design phase will then build the loop according to whatever has been decided in your requirements. And then during installation commissioning, you can also say, well, it will apply also there. Of course, you will need to install and commission the system as per your requirements, and you will have to validate that. But mainly, the topic that we tackled here today is also of interest for the operator and maintenance engineers out there that is listening in to this webinar. Because if you need to make a maintenance or if you need to make a repair on one of those redundant architectures, you better very well understand how the architecture potentially can either jeopardize your safety behavior of your system and or potentially bring your process availability into a certain, let's say, unavailable potential reason that if there would be coming in a spurious trip, that you may lose your production. And of course, it goes without saying that we also need to take care of that during the modifications. What Gabriele has mentioned is that we did receive some questions during the pre-registration. I took the liberty to select a few of those questions, so we have a second presentation after the main presentation where we actually will answer some of those questions that came in during the registrations. What I just explained you there in words is here actually being put into text. That means that where and when do you define or decide or how to use those architectures? Well, in the definition phases, which is in the phase number 1. So when you have your PHRA, your process hazard risk assessment, that is where you first will look what potential hazards do we have. What are the potential consequences and the likelihoods? What is acceptable for us or not? And based on this, you go into a second phase, which is then called the LOPA or layer of protection analysis phase. And there you will allocate your safety functions to some existing layers or to some existing systems that you may or may not have yet. If you don't have it yet, clearly, if you need some extra risk reduction, that is where your first safety requirement specification definition will come in. And there you will define what safety instrument function do I need enabled to prevent this hazard from happening in my production unit. So your safety requirement specification, clearly that is the first requirement that will actually ask you, you will have to have a minimum hardware fault tolerance equal to 0. That means you can build that with a single 1/1 architecture, or you need to have an HFT equal to 1. HFT stands, of course, for hardware fault tolerance. In other words, how many danger failures can my safety loop tolerate and still achieve my safety function. Once you go into the deciding phase, that means that here you will start to design the system. That means that you will go into the design and engineering of your safety instrumented system. Clearly there you need to know exactly what hardware fault tolerance is required according to your requirement specification. And that is actually what we are referring to here in the second bullet, where we say either you will use, if you use something called Road 1H, and we do have another webinar that is handling those Road 1H versus Road 2H. So if you are handling a Road 1H according to the IEC 61508, which is the other functional safety standard for the manufacturers, like GMI as an example, if GMI is building a SIL-X, let's say, interface, the SIL-X interface needs to apply to a certain requirement from the hardware session and or the software session from the 61508. And one of those requirements is, of course, called the hardware fault tolerance. Another method for the 61508 would be the proven in use, which we call the Road 2H. And the Road 2H will use the same table as you do in the IEC 61511. Again, we have a webinar on this. This is the famous table 6. And I do remember somewhere in the slides coming up, I think it's in the Q&A slides or maybe in this one, we will actually show you the table 6 as well as the Road 1H tables 2 and 3 from the 61508. And then at last, you go to the end users, to the operating companies. Of course, the operators and also the maintenance engineers will need to know exactly how the architecture can, for instance, degrade from a higher mode to from a 2 out of 3 into a lower mode. That's why we call it mode of degradation, into a 1 out of 2 or into a 1 out of 1. That's the table that I was just referring to. So on the left bottom corner here, we show here a table which is called type A and type B. And again, that is very specific information that you will find on the, let's say, data sheets or in the safety manual from the manufacturers. So when the manufacturers like GMI will provide you with a SIL compliant interface, well then normative required from the 61508 is that the manufacturer shall provide you with a safety manual. In that safety manual will be very key, let's say, items be mentioned, such as, for instance, they will tell you if it is a type A or a type B device or an interface. They need to give you mandatory obliged a safety manual, and they often give you, here between brackets, a certificate / a report. A certificate is not normative required by the standard, but that is what we see in the industry, that vendors will give you a certificate that is then based on a third-party assessment from another company that has made an assessment of their devices to prove evidence that the assessment complies with the 61508. That's all called the Road 1H. In a nutshell, I call this the theory approach. So that means that if a GMI would start with a brand new device which has no records in the field, the only way to do that is to start with method number 1 or this Road 1H. The methods naming convention is purely my own name from during my training courses. I have called this method number 1, but that is not how it is called in the 61508. They purely call it Road 1H. And here in the table type A and type B, this is table 2 and 3. Type A versus type B, you will see that here we have a column where you can recognize a number 0, 1, and 2. And that is a topic that we will handle here today, which is here the title, hardware fault tolerance, or in other words, it will give you the hardware safety integrity architectural constraints for your specific SIL requirements. So you see the SIL requirements here in the bottom columns. And on the left column here, that is either this is your diagnostic coverage in your devices and or this is your safe failure fraction. The higher the coverage, the higher the safe failure fraction, the lower the number in hardware fault tolerance for a higher SIL level. Opposite, the lower the safe failure fraction, the more of them you will have to install to achieve a higher SIL level. If I move to the middle, here we go into the story of proven in use. That means that the manufacturer needs to collect and prove the quality of the data collected based on the field records from, let's say, an installed based experience of valid data that they retrieve back from the field. That is the proven in use story, which is often used now as Road to H on some of the certificates. And even so, the Road 1H and Road to H for some manufacturers is being mixed. The last one here on the right branch, that is called the prior use. That means that's the end user's quality feedback validator from an installed base, but you need to be able to prove that. And there are two guidance giving in the standard, the 6.15.11. One is here called report number 4, which has been revised. So the new date should be here 2020. That means that when the edition 2 came out of the 6.15.11, they cannot refer to the future. That means we have adopted this, of course, now in our training courses. Here we are referring to the report 4 of 2020. And here it's the Namur NE 130, which is a guideline that has also been revised by memory in July 2023. So that's very recently been revised. Those are two guidance on how to collect valid data. So both proven in use and prior use means the installation exists and you have good quality valid data. And if you can prove that, either prior use or proven in use, then you are allowed to use this table, which is a simplified table called table 6. And table 6 is coming from the IEC 6.15.11. And again, there we see the hardware fault tolerance. We see here the 0, which is the same 0 as on the left table A and type B table. It's the same number 1 and it's the same number 2. And that's the topic that I selected for you. So that's here just my summary. Road 1H is a theory approach. Road 2H is the quality feedback from the field devices, either from the manufacturers that they retrieve it back from the end users or from the end user itself. But I do know, that's why I'm also hinting here, I do know it's very rare to find good quality valid data. And there are many reasons for that, which I will not go into more details, but we do have a problem that our quality data from the field is typically not as good quality as we would hope for. Summary on the hardware fault tolerance. And I make two tables for you. The middle table, that's all about safety. The right-hand table, it's all about making production, making turnover. That is your production availability. And as you see over here in the middle here, we see here a 1 out of 1. That means if there is a requirement to build a hardware fault tolerance equal to 1, that means your architecture for your safety loop can be chosen to be a 1 out of 1. That's the architecture for safety availability. In other words, if this one instrument, this one channel, this one sensor will fail, your safety function will not be available anymore. That is what the HFT0 is asking you over here. If, however, you like to also try to give production availability with an HFT equal to 0, that is where we would tend to go into an architecture of a 2 out of 2. That means you have two devices, but both have to agree with each other before you execute your demand or before you execute or achieve your safety function. Well, with a 2 out of 2, clearly, if there is one danger failure in there, you cannot achieve, and I will show you some practical example later on the slide, you cannot achieve your, let's say, your demand anymore on your safety function. So both a 1 out of 1 is not good for safety, as well as a 2 out of 2 is not good for safety, but you would only go into a 2 out of 2 if you want to increase your production availability, because in this right-hand table, you can tolerate one spurious strip and not shutting down, whereas here in a 1 out of 1, you cannot tolerate a spurious strip clearly because you will lose your production availability. But both installations with the HFT0, that is the number or the digit 0 for you, you cannot tolerate any danger failure. When you see an HFT of 1, that means clearly or simply speaking, we need to tolerate one danger failure. It means now you have two devices. only one of them needs to be functioning correctly before you will achieve your safety function. That means in that case, if the other channel would have a danger failure, well, we can tolerate that. That is what this number 1 means here for us in the left-hand table. Most of you will recognize a 2 out of 3 on your sensing, on your measuring devices. And the reason that they go for a 2 out of 3 is not because of the safety availability, it is purely because of the production availability. Because if there is one spirit strip coming into this 1 out of 2, you will still trip your unit. If there is one spirit strip coming into a 2 out of 3, you will not trip your production unit because you will wait until a second trip comes in before you trip that unit. And last but not least, we have a 2 HFT. That means in HFT2, I can have a 1 out of 3. That means I can have now one device coming in out of the 3, and I will actually carry out my safety function. That also means opposite, we can have 2 other ones with a danger failure, and I can still execute my safety demand. The second column over here is a architecture for production availability. That's a 2 out of 4. And again, I will show you some examples on one of my next examples. I see that there's a question coming in. That question that just came in, can you clarify safety availability versus production availability when the safety device is taken on maintenance? I will try to do that, but please give me first a few more slides, and hopefully then your question will be cleared without me putting some words on it. Architecture in both standard is expressed as an M out of N. The first letter M, that is your voting independent channels. The last letter N, that's your total number of redundant channels. And that's typically how we will express that. And I'm pretty sure you are familiar with a 1 out of 1, a 1 out of 2, 2 out of 3, maybe 2 out of 2. Rarely you would see 2 out of 4s, or maybe if you are more in fire and gas, then you can have a 2 out of X, or even a 3 out of X, or whatever it's going to be. It's always the first digit is your independent channels that needs to agree with each other, whereas your last channel is your redundant available channels. Right, let me give you a practical example because that may all sound a bit like theory. So let's put it into words, into a picture, which is easy or easier to understand than maybe all the words we have just explained. I got here a reactor with an inlet. Let's say we have a product coming in through this pipeline, and we are isolating this with 2 valves. We have 2 fail to close valves. That means the safety function is close. It's to isolate the stream for not filling up that reactor. We call this here a 1 out of 2. Safety people, typically, they prefer that. Why? Because if this one valve is stuck open and I can still close the other one, I can still isolate my stream. I can still go into a safety position. However, if this one valve will close for no reason, that means a spirit strip. Production people hate that typically because they can lose their production with one spirit strip in either one of those 2 valves. So the conclusion is a 1 out of 2 for us. It's great for safety. However, it's the worst nightmare for the production people because if one of the 2 will actually trip for no reason or close for no reason, you lose your production. In the same story, in the same context, we take the same reactor and now we go into the drain line. So we want to drain the product and we're using 2 valves again, but not fail to close, we're using fail to open valves. That means that now we need to open both valves, enable to drain. Why would we do that? Well, clearly, that is what production people would prefer because if one valve starts to leak, the other one may be still isolating it and the drain will not lose all their production. The safety person typically will not like this because the safety engineer will very quickly understand that if this valve here is, for instance, stuck closed and they want to open to drain it, no matter how many other valves we have installed there, we can never drain the production. So it's great for the production availability because if one valve goes spuriously open, you may not lose your production because the second one is still protecting it or is still maintaining your production availability. Opposite, if this one valve is stuck closed, and you can still open the second valve, you cannot drain. That means it's the worst situation for safety, but it's great for production. So somehow we need to keep the production people, of course, happy. We need to make the production, plus also need to try to protect it towards safety. So how do we combine the safety availability on the left-hand side with the production availability on the right-hand side? And there are many different fancy configurations that we could show you as an example. But before we do that, let me first ask you a question. That's the first poll question for Gabriele.
Yes.
You may launch and I will read the question. And that's also one of the questions that came into the Q&A already. So safety availability versus production availability. And only one answer is the most complete and the most correct answer. So answer A, 1 out of 2 and 2 out of 3 are the same for production availability. For someone that just listened would quickly know the answer. B, 1 out of 2 is better for safety availability than the 2 out of 3. Answer C, a 2 out of 3 provide both safety and production availability. Answer D, 2 out of 2 and a 2 out of 3 provides the same safety and production availability. And then answer E, 2 out of 2, 2 out of 3, and 2 out of 4, all architectures provide the maximum safety and production availability. So we need a few more clicks because we don't like audience that are asleep already. So click on any button just to show that you're still alive. That's helping us already.
Getting close to 60%. Wait a little more.
We have an active audience, although it's well, it's not Monday morning, it is Tuesday morning. But there was yesterday a public holiday where I'm in today, so for me it's my first working day. So I'm still in the Monday morning mood.
Well, I suppose we can stop. We reached almost 80%. So and share results.
Okay, so well, right. No one answered number 1, which is 1 out of 2 and 2 out of 3 are the same for production availability. Of course, that is absolutely wrong. Then we have quite some people click that 1 out of 2 is better for safety availability than a 2 out of 3. Well, it's a bit of play with words on safety availability. If you purely look on the hardware fault tolerance, they are identical. They both can tolerate only one danger failure. If you look in reliability, in calculating the PFD for such loop, of course, that is where there will be a difference. Answer C, 2 out of 3 provides both safety and production availability. Well, luckily here in our webinar, the majority have selected this answer C. That would also be my personal choice if I would read those questions and I have to collect or select the most correct and the most complete answer. Then answer D, why is answer D totally wrong? Because a 2 out of 2 has nothing to do with safety, only production availability. That's also why answer E is also, unfortunately, totally wrong, as 2 out of 2 gives you no safety. So both answer D and E, it's a 2 out of 2 who is killing the entire sentence. So you don't even need to bother to read the rest. They are both having no safety availability. Right, so stop sharing this. Let me move on. I made here a definition, the bottom one, not by the IEC standard, but by my own definition. And I have defined in the next slide a column which is called HFT, and I put it here in a green color because I used the word S. So I will actually define here a column in all the architectures to show you what is the hardware fault tolerance safe or spurious strip versus what is by standard IEC standard on the safety standard. Then they are talking about HFT, and I put here between brackets D for dangerous. The IEC standard doesn't care about spurious strips. The IEC standard is there to make something safe. The IEC standard is not there to make money with your production. Production people, of course, they care about production. Safety people, they care about safety. That is why the IEC standard only focus on HFT for danger failures. But since we are in the industry trying to also produce some product to make some money, to keep our management happy. That means also need to take care of the production availability. And that's why I have made here the following summary table. So let me take you through the table. On the left column, that's all the different architectures that we have mentioned so far. The first column is always the first digit or the first letter or number from your architecture. That is your voting number. So when you see a 1 out of 1, one channel needs to be active and able to do something. If you see a 2 out of 2, two channels, that's the voting 2 that you recognize in here. The second column is called the redundancy column. And the redundancy column, if you look on line number 3, 4, 5, and 6, that is where you see always the last digit or the last number that you recognize here in your architecture. But there is an exception. When your voting, your 1, is equal to your redundant number 1 at the end, your safety redundancy becomes 0. That means when I have a million, but I need a million to do something, you have 0 redundancy in a million out of a million. Or if you have a 10 out of 10, you have 0 redundancy because you have 10, but you need 10 to do something. So there is no redundancy in a 1 out of 1 and in a 2 out of 2, or in anything where voting is equal to redundant, there is 0 redundancy. Now, what is the most important column for you here in this webinar and also in the future in your architecture of your field devices or in your safety loop architectures? It's the red column over here, which is called HFT by standard definition. And by my own definition, I put between brackets dangerous to make it really clear difference between this column with the last right column here on the right. If you look to the hardware fault tolerance dangerous, you can see that both a 1 out of 1 and a 2 out of 2, they can both tolerate 0 danger failures. A 1 out of 2 and a 2 out of 3 can both identically only tolerate 1 danger failure. But why would you now select 3 sensors if you can do the same with 2 sensors in terms of hardware fault tolerance? It's because of the right-hand column over here. You can see that now in my 2 out of 3 column, I put a 1 under the superior strip or the safe failure. That means in this particular architecture, you can tolerate 1 superior strip and still maintain your production availability. I give you here a small hint or the trick how to come to this last column. You take your voting channel -1. That gives you the number here of superior strip in this right-hand column. So I give you an example. I have here a 1 out of 2, and I simulate here a hardware fault tolerance equal to 1. That's the danger failure. So danger failure means that in normal conditions, I take here a lamp, I take here a battery, I take 2 normally open contacts. When I close this loop, that means both contacts are working correctly or both sensors in 1 of 2 are working correctly. There is no reason to trip. Trip would mean open the contact, turn off the light. That is your safety functionality when I can turn off the power to this lamp. So if I either open 1 or I open B, A or B, either of them can actually stop the production from running. That also means that if one of those two, assume that, for instance, your sensor B or your input channel B has a danger failure, I can still open A and I can still stop my production. However, assume that A would be spurious, would go open for no reason, you will lose your production. So that's what we say as a summary over here. You cannot tolerate any spurious strip, but you can tolerate 1 danger failure. I make the same with the 2 out of 3. So 2 out of 3, we have 2 contacts A, they work both together. Both B is working together and both C is working together. So in normal condition, everything is closed. What do we show here in the third example over here? That we open B, so that means B is, for instance, spurious open. So B goes open for no reason. As long there is no A and no C going open, you will not trip your functionality. That means we need to open the second contact like we do over here. So we opened here C. So as you can see in this branch, since now B was spurious open, and C is now going open on demand, that is the signal coming in. So we have 2 out of 3 open. We will trip the functionality regardless if A would have been, for instance, dangerous or not. So here we made A dangerous. That means A cannot work anymore. As long that we can still open the second contact and there was one contact open already, you can trip that functionality. And that's the difference between the 1 out of 2 and the 2 out of 3, that with the 2 out of 3, you can at the same time simultaneously tolerate a spirit strip and also one danger feather. Now let us compare a 1 out of 2 and a 2 out of 3. I made here a binary table. So the column A is the same, the column B is the same. Of course, here with a 3 channel, we add 4 additional lines in here. So we have 8 different combinations that can create a shutdown. And if you look here, when A and B, both of them are 0, you will shut down. If either B or A is 0, you will also shut down. If you go on the right-hand side, you can see here, if for instance, in this particular case, here we have only B shutting down, or we have only C shutting down in line 4, or we have only A shutting down in line 7. So here we're looking at line 4, line 6, and line 7. We keep the production running regardless if there is already one spurious strip or one shutdown coming in. So here we will wait until the second one comes in before we will shut down. So in this particular column, in a 2 out of 3, you need to find 2 zeros in here in either A, B, and C together. We need to find minimum 2 zeros before you will go into a shutdown. That gives you the benefit here with a 2 out of 3 versus here a 1 out of 2. And to come back on the answer on this question earlier, what will be the benefit for maintenance purpose, etc.? I have made a slide in the Q&A because that question was also already coming in into a pre-registration. Yes, Gabriele, we have the last poll question. The
We
second
also
poll.
have another question in the Q&A session. Maybe we can see it later. I can launch the poll at this time. So bypassing, there you are.
Okay, I will read the question loud for the rest. So when you were presenting architecture constraint HFT, then there was method 3, 6, 15, 11. Okay, that is based on row to H, which is the prior use, correct. Table with diagnostic coverage greater than or equal to 60%. No, that was in the edition 1. Edition 1, the table 6 was between 60 to 90%. Because somehow the committees decided that the safe failure fraction or diagnostic coverage on all devices will be between 60 to 90%. That has been removed in the edition 2 of the SIG 1511. That means safe failure fraction is no longer linked to the table 6 of the standard. Safe failure fraction, I call this in my own words, has been put on the back burner because the safe failure fraction did have some problems in the industry in terms of that some manufacturers were going sky high in safe failure fraction, as there is some mathematic modeling between the safe failure fraction possible to have a lot of safe failures, not many danger failures to bring your coverage or to bring your safe failure fraction, let's say percentage ratio, into a very high number. That is why edition 2, to make a long story short, prefer to have quality feedback data regardless what safe failure fraction you have. So table 6 in addition to is no longer linked to the safe failure fraction and or diagnostic coverage as it used to be in the edition number 1. So we have answered this live. I can click on this one. All right, so let me read quickly the question now on the poll question. Bypassing one channel of a 2 out of 3 voltage block in a SAT PLC can always be done by simply disabling one input channel. Well, for those who have clicked this answer A, to be blunt with you, I think that is a serious problem if you would actually believe that is correct. That is certainly not correct. So I would certainly not do that. Can only be done, answer B, after compensating measures are in place and degrading to a 1 out of 2 for a time-limited operation. That sounds very attractive to me, especially the word compensating measures in there. Because as you may know or not know, edition 2 will allow a bypass as long as you can compensate for whatever channel that you will disable or bypass. That's the new topic by the edition 2. Well, new. It's 2016-17, so it's old by now, but it's still in the latest edition of the current edition 6.15.11. Compensating measures are required before you allow anyone to put a bypass on on one of the channels or one of the measurements. Plus also, your bypass must be time limited, because the time limited will also be taken into account for your safety availability calculation, known as your reliability or your SIL estimation. Answer C cannot take place while the process needs the safety protection on a live production facility. Well, we all know that in the industry, there is no plant in the world with no bypass on. There's always a reason why they have to put a bypass on. So that will always be, I call that the necessary evil in our industry, because we always have somewhere a bypass on, but that needs to be, of course, controlled, managed, time limited, etc. And compensating measures needs to be in place. So answer B was indeed here the correct one. And answer D can be solved via two redundant one of two solutions. Well, not really, and I will try to show that also in one of the next slides. None of the above. Well, E is not been has been clicked by someone. Okay, well, that's also not correct. So here the only correct answer was the majority of the group here should be answer B with the compensating measures. All right, so stop sharing this. Let me continue. Right. This is coming out of a, let's say, a question that I somehow got through one of my training sessions, where a end user was of the belief that in his particular brand related safety PLC, that he could actually bypass an input without having to do anything on the safety PLC functionality of degradation, where I told him, well, let's compare that. So if you look here back to the table, which you already have seen, the 1 out of 2 on the left-hand side with the 2 out of 3, what is the difference? Here we have only 2 channels, here we have 3 channels. So assume that you take a 2 out of 3 and you simply disable one of those channels, and you start to believe that therefore you have now a 1 out of 2. Well, if you look into this table over here, there is a problem, because that's only possible if you would disable channel A or channel B or channel C. Your function block initially needs to degrade into a 1 out of 2 if you want to maintain the same safety. Otherwise, assume that you disable channel C over here and you leave the block for what it is. That means both channels A and B in this particular case will have to come in, because that's all a 1 over here. That means you are in that situation on 5, 6, 7, and 8, because you disable C into a healthy condition. That means now your condition, instead of a 2 out of 3, becomes a 2 out of 2, because your channel A and B both have to go into a 0 channel or a 0 condition before you will shut down. That's what we say over here in this red text, and I made an explanation on this on the next slide. That means that if you would have disabled C into a healthy condition, you recognize line 5, 6, 7, and 8 is actually the same here as in a 2 out of 2. That means that now both channels needs to come in as a 0 condition before you will carry out your safety function. So to make a long story short, when you disable a channel, either A, B, or C on a 2 out of 3 function block, and the function block in your safety PLC doesn't go into a degradation into a 1 out of 2 for a time limited condition, whatever, your functionality becomes automatically a 2 out of 2. That means the other 2 channels needs to trip before your safety function will start to come in. What is there the biggest, let's say, danger or fear that we have? Assume that one of the channels A or B in the 2 out of 2 configuration has a danger failure, you will never be able to trip. In other words, you will always maintain production in a 2 out of 2 if one of the 2 channels has a hidden danger failure. And that's why we are saying that you need to take care, if you do some maintenance, if you do some repair on a 2 out of 3, please think about that during the time period that one of your channels is no more live, that you potentially have a 2 out of 2 in front of you and not a 1 out of 2 as some people were thinking. So the only correct, that's a conclusion, the only correct method to bypass one input channel on a 2 out of 3 voting structure is to degrade your architecture from a 2 out of 3 into a 1 out of 2, maintaining the same architectural constraint HFT equal to 1, and the safety availability, but there is no more production availability if you go into a 1 out of 2. That means from production availability point of view, if you have one spirit strip coming in, you will trip. So we do know when you degrade from a 2 out of 3 into a 1 out of 2, you take the advantage of production availability away and you only monitor your safety availability. We have made some questions and answers on the next slide. Let me first summarize here our webinar. What I would like to give as a small advice to most engineers, make sure you first understand the basics, the foundation of the architectures of your safety loops before you start to play around on such type of configuration. Select the correct architecture based on either this table 6, and as someone already was asking, there's no longer safe failure fraction of diagnostic coverage being required in that table 6. What is required? Quality data, your data, and not someone else's data, not a commercial database, not a vendor data. It's your quality feedback data from the field is the preference for the 6, 15, 11. We are talking about the data uncertainties on the failure data of your equipment. Truly understand the difference between safety availability versus production availability. Well, if you go back to the table with my HFT dangerous and HFTS, that table will give you a very good foundation to understand the architecture, I do hope. Respect the bypass requirements from the IEC 6, 15, 11 in terms of compensating and in terms of time limited. And of course, keep it functional safe and think twice before you act. We as GMI, we can support you with a book which is called the SIL Manual 4th edition. In that edition, I was the co-author for Chapter 7 and Chapter 8. Chapter 7 is the IEC 6, 15, 11 Executive Summary. And Chapter 8 is a one safety loop, one safety instrument function description called a safety requirement specification example. We do have also a link here to the GMI website where you can see a GMI pre-recorded session. But as Gabriele was just already mentioning, all our webinars are being recorded and will be available on a YouTube channel. We also support you, of course, with our TOV Rhineland accredited training courses. So I'm still an accredited licensed course provider for TOV Rhineland, not only for functional safety, but we just finished 2 weeks ago here, we just finished our first cybersecurity risk assessment combined training course. So we are also delivering those type of training courses. And we also provide services. So one of the services is either function safety management or function safety assessments. I'm in the meantime working on a very large function safety assessment for the biggest project ever here in Europe on a ethylene cracker. We also do 62443 lifecycle operation technology risk assessment support with customers. And that's it. So let me take the liberty to go back into your other presentation. I'm just looking for my other presentation. I got too many windows open as usual. So which one is it? I think that is the Q&A. Let me share that one. Right. So, that's a long question. Let me first read that long question. Oops. I got a window blocking my text, so I'm just trying to read. Okay, Mr. Zoom, thank you for blocking my text. Okay, there is an issue bubbling up from time to time. 3 redundant transmitters being used for BPCS control loop and SIF. From the initial 2 out of 3, it may be better to identify one dedicated transmitter for the BPCS control loop and keeping the remaining ones for a 1 out of 2 or as a 1 out of 2. Well, as you just have seen already in our webinar, but I have repeated this in here, regardless what we just explained. So we just repeat it again. There is, of course, a difference between a full 2 out of 3 for a SIS or for a safety estimated system functionality, or a 1 out of 2 with one additional transmitter for the BPCS. However, there are maybe some alternative solutions that I may try to explain. I'm just reading here another question that comes in. I'll read this in a minute. Let me first focus on this one. You see here on the left an example with 3 transmitters, 3 temperature transmitters. They are going in a clear 2 out of 3 function block inside your safety instrumented system. So we just explained, I will not repeat this. What is the benefit of having a 2 out of 3? You can tolerate one danger failure in one of those transmitters, and you can tolerate simultaneously another transmitter having a spurious strip. That would be the benefit for a 2 out of 3. If I would go into the question and I would say, let's take 2 transmitters and we go into a 1 out of 2, that means from a hardware fault tolerance danger failure, we can still tolerate either in this 101 or 102 transmitter a danger failure and still achieve our safety if the other transmitter comes in to ask us to trip. However, if one spurious strip comes in, we will be gone. That means that assuming that in a 2 out of 3 transmitter configuration on a, let's say a pipeline as an example, one transmitter goes in straight into your BPCS to control maybe the temperature controller on that specific process. Well, that would be the disadvantage in this specific situation, that here we would have one spurious strip shutting down my production availability. I have seen over the years something like this. We use the initial 2 out of 3 transmitters first for the trip sensation or the trip functionality in my safety instrumented function in my 2 out of 3. But I may, as an example, I may copy one of those transmitters into an analog signal, and we take the analog signal then to control the process also. And that has some tricks in terms of, for instance, if you would do LOPA as an example, that means that we can only take credit here for the safety instrumented function. If for whatever reason, we also would take credit for the BPCS, and we take already a risk reduction factor here for the BPCS, we cannot use the same transmitter and for safety risk reduction factor and for a risk reduction factor on the BPCS layer. We could not do that. But we could use this as an example if we want to save potentially some money, and we would still go into a 2 out of 3, giving the production people the benefit we can tolerate the spurious strip, and at the same time, we can make some of those signals available to also control maybe my control valve. That's purely an example. So there are many different ways that I can show you the example, but that's something like a common example that we have come across in the industry. As I mentioned already here, the spurious strip is the only disadvantage that you will have in that particular middle situation or example. Another person during the registration was asking, does this mean ways to do online proof testing maintenance without degradation? Well, again, I also already have answered that, but I will do this again over here. As discussed during the webinar, if you correctly mask your inputs, A, B, or C, regardless which one it is, and you degrade into one of 2, that means that during your maintenance, during your calibration for testing, you could potentially do that. But you have to make sure that you go first into a 1 of 2. So here I took again the sensor 101 and 102 into a active situation that they are now protecting still the facilities in a 1 out of 2. You would disable and go in your function block first in a 1 of 2. You would disable your third input, and you would use it only for test purposes. That is what you potentially could do, again, only if you go in the right, let's say, degradation modus on your function block. Right, let me first read the questions loud for you. One attendee is asking, when one channel is bypassed in 2 out of 3 and spurious strip comes during bypass, how can we mitigate the risk? Well, please clarify yourself. Is your spurious strip coming into this one channel that is in bypass, or is the spurious strip coming into the 2 out of 3, which goes into 1 out of 2? So let me take that example over here. Assume that you do the correct, so I go back, you are having a 2 out of 3. You want to do maintenance on the transmitter number 100 over here. That means you degrade into a 1 out of 2. So if there is a spurious strip coming into either 1 out of 1 or 1 out of 2, you will lose your production and you will go into a safety position. So will you still mitigate the risk in this particular case? Yes. Of course, you need to ask the question, how did my spurious trip comes in? Was a spurious trip based, as the word is saying, spurious nuisance trip, because of the malfunction of a transmitter shutting down the production? You still go to a safe position, mitigating your risk. Of course, you lose the production. And that's something that needs to be considered. If you have a 1 out of 2, you cannot tolerate a spurious trip. There was a second question. It's rather a long question, but I will try to read all of it. In a 2 out of 3 voting scenario of, let's say, 3 transmitters, if we have a fault or inhibit applied to the A transmitter, does automatic voting degradation go from 2 out of 3 to 1 out of 2, ... In other words, that will be depending on what type of safety PLC function block, vendor, brand you are using. So you better ask this to your vendor specialist to declare or justify or prove this to you. And then this person continues, I would have thought this would depend on the control system, as some legacy system doesn't have the capability. Example giving, when inhibiting the logic on the A transmitter, it holds the alarm trip serial healthy. Well, that's exactly this person asking this question. That's exactly what I was trying to explain the entire time, that these legacy systems do have a problem that some engineers don't realize. By bypassing, or like in your question, by inhibiting this one channel, and your function block in your legacy system has not been degraded into a 1 out of 2, as I just have proven you, you have a 2 out of 2 for the duration of inhibiting this one channel. In other words, you have no safety functionality available, in the sense of, if one of those 2 sensors will ask you to trip, you will not trip until the second one comes in. And the danger is, in that particular example, if the second channel has a danger hidden failure in that sensor, you will never trip and you are not protected any longer. So that's certainly something we ask the attention here with this webinar to look at. And the last one from a person coming in, so it's like a free consultancy time. Can we go to 2 out of 2 when doing maintenance on a 2 out of 3? Well, the person asking the question, if you are on the production side of the story and you like to keep your production running and you don't care about safety, yes, you can go to a 2 out of 2. But if you ask me as a safety person, I would not advise this. I would strongly advise to degrade into a 1 out of 2 if you care about safety. If you only care about maintaining your production, regardless what your safety position is, then you can go into a 2 out of 2. But I can tell you, I would not like to be an engineer on this site if that is the culture of your production people, only caring to run production and don't care about safety. Right, last question and last answer from me, and then we nearly hit the 60 minutes. Actually, we are over 60 minutes. Does the approach differ with different degradation of voting configuration? Let me read this again. Does the approach differ with different degradation of voting configuration? Well, I think no. It depends on, of course, which configuration or different degradation you have in mind. What I answer here is actually what I still stand behind. You need to understand first the basics of this table. If you do start to understand the red table, which is your HFT dangerous, and you do understand the left-hand configuration architecture column, take the last column on the right-hand side with it, that's your spurious strip. If you understand both the red and the green table, then you will certainly be answered your own question, because that is the answer to all the different configurations that you may come across in the industry. All right. Oh, there is one more question. That question came in very late, so I added, how degradation 2 out of 3 to 1 out of 2 affect the SIL? Well, of course, it will affect the SIL, and I have tried to answer this in a summary over here. Both 2 out of 3 and 1 out of 2 configuration have the same hardware fault tolerance. That should be clear by now. Second bullet, a 2 out of 3 has a lower PFD. That's the probability to fail on demand That's your availability calculation on your system, because a 2 out of 3 requires 2 failures for the system failure, whereas a 1 out of 2 requires only 1 failure. So as a result, degrading from a 2 out of 3 into a 1 out of 2 will increase the availability calculation or the PFD calculation, and therefore will decreases the SIL number. And I've given this table here below, even though both have the same hardware fault tolerance. So summary, if your PFD number starts to go lower towards the bottom over here, your SIL number will start to go higher. So as PFD is increasing, your SIL number will start to decrease. And therefore we say when you have a 2 out of 3 with a lower PFD number, because you need to have 2 channels to come in before you will trip over here. If you only have a 1 out of 2, only 1 channel can go into a, let's say, trip function. That means that if you would do the mathematics calculation on a 1 out of 2, you will recognize that your PFD will tend to go into the higher numbers. The higher numbers for us means the lower SIL numbers. Opposite, the lower PFD numbers goes into the higher SIL. So short answer, yes, a 2 out of 3 degradation in 1 of 2 can potentially also affect the SIL. It all depends, of course, where in your SIL performance band you were sitting before in 2 out of 3, before we can decide that potentially you go into a lower SIL degradation. Right, that's it. Finito. I will give the word back to
We have a question now for everybody.
okay. Oh, you have a question. Okay.
Yes, I have one for our participants, so it's probably the most important, you know.
Yeah, I typically joke. I said my invoice is based on the rating here, but that's of course not true.
We will be judged based on these results.
Okay. Well, I was surprised in this webinar how many participants remained in the webinar session. That is good. So thank you for that. And also thank you for posting many different small questions, all related to the same topic. I think we're nearly there, Gabriele. I think you can share.
Yes, I closed it. Do you want me to share the results?
Yeah. Yeah, you can click on sharing. Thank you.
There it is. Thanks.
All right. So I would like to thank GMI for giving another opportunity to share some of the topics that we like to talk about with engineers. And thank you for all those who came in on the webinar and stayed on the webinar and posted all those questions. I hope it was useful for you. And as Gabriele promised, you will get, for those who still are remaining online, you will get either an evidence that you remained online in terms of a participation certificate, plus also you will have the PDF version of the slides that we presented, and you can also listen again to this webinar on the YouTube channel. So thank you, Gabriele. Thank you, everyone.
Thank you, Tino. Thank you, everyone. And have a great day.
Thank you. You too. Ciao, ciao.
Ciao. Bye.
Bye.